So after being introduced to radical functions, section 18.3 talks about simplifying radical expressions. So what do we mean by simplifying? Well, we're going to develop a rule here. Let's say that we have the nth root of a times b. Now, from our previous lesson, we know that we can rewrite an nth root as what kind of power? How can I rewrite an nth root? As a fraction power, 1 over n. Right? You guys recall? It's like it's going to matter. Once you have it in its exponential form, you can deal with that piece by piece. So in this case, that means a to the 1 over n, b to the 1 over n. You guys agree? That's just a regular exponential rule. But again, what does the 1 over nth power mean? What is a 1 over n power? What does it mean? It's the nth root. So this means nth root of a times nth root of b. So we've developed here a rule for radicals. All right? We have a rule here for radicals that says if you have multiplication underneath a radical, you can break that radical up into each of the factors. All right? Before, we didn't have any radical rules. The only thing we could do was change it to its exponential form and use those exponential rules. Now we're starting to develop some rules just on the radicals themselves. So, multiplication inside a radical can be broken apart. So let's say I have the square root of 55. Isn't 55 5 times 11? So according to this rule, I can rewrite this as the square root of 5 times the square root of 11. That's what this rule says. You guys agree? What if I had the square root of 45? Well, 45 would be 9 times 5. Is that so? So I could rewrite this as square root of 9 times the square root of 5. What's different about this one, though? Yeah, 9 has a very nice principal square root. The principal square root of 9 is 3. What if I wanted the cube root of 16? (16) is 8 times 2, right? So according to this rule, I could rewrite it as what? Cube root of 8 times cube root of 2. But the cube root of 8 is 2. So I can write this as 2 times cube root of 2. All right, so we've seen this property illustrated. In the top example, it wasn't particularly useful. In the second and third example, however, it wound up being useful. And what made it useful in those cases? In the second one, we had a perfect square. Isn't 9 a perfect square? And in the third one, we had a perfect cube. And that's what made that nice. So when we talk about simplifying, this is what we're referring to. We'll consider a radical expression simplified under these 3 conditions. The radicand has no factor raised to a power greater than or equal to the index. The radicand does not contain a fraction, and there are no radicals in the denominator of a fraction. So if we look back, cube root of 16 was not simplified because isn't 16 2 to the 4th power? 16 is 2 to the 4th. But then don't I actually have a power inside that's bigger than the root? So that's what number 1 means. You can have no factor raised to a power greater than or equal to the index. All right? We also don't want the radicand to contain a fraction. You guys are allergic anyway. And we don't want radicals in the denominator, which we're going to have to deal with in a later section. All right? But just bear in mind that's out there. Now, if we approach this in the book way, they want you to recognize when you're dealing with perfect squares and perfect cubes, but not just like recognizing that 9 is a perfect square, but recognizing that within 72, don't you have a perfect square?
Yes.
Yeah, you do.
I don't know what it is. I'm trying to figure that out.
36.
Okay.
All right? But you've illustrated the point. Is it really easy to see some of those perfect squares? Not really. So what about perfect cubes? Do you even know your perfect cubes?
No.
What's 3 cubed? 27. 4 cubed?
64.
It is 64. 5 cubed?
125.
125. 6 cubed? You tap out. Okay. So I understand perfectly. So when we are simplifying radicals, write each number as its prime factorization. The fundamental theorem of arithmetic says that any number can be broken down into a unique set of prime numbers. All right? And we've even tasted this a little bit before when we were breaking numbers down, and that was when I was showing you how to find the LCD. All right? So for example, if I have $24. Let's break this down into its prime factorization. So what times what gives you 24? Okay. All right. All right. So we're going to avoid the 1 case, but 8 times 3 is true. Also 6 times 4. Okay. 8 is 2 times 2 times 2, isn't it? You guys agree? So this means 24 is 2 cubed times 3 to the 1st. That is its prime factorization. But wait, you say. What if we had done 6 and 4? Well, what does 6 break down into? 3 times 2. Whereas 4 breaks down into 2 times 2. And we wind up with 2 cubed times 3 to the 1st. Do you guys see? So if we were looking to simplify a square root, you'd have to go through the bottom route, recognizing that 4 was the perfect square contained within that number. And if you can do that, that's fine, right? But if you can't, then the good news is it doesn't matter how you break it down as long as you break it all the way down to its primes. Now, remember, what cancels out an nth root from last class? What canceled out an nth root? An nth power. So what would cancel out a square root? A square. Do I have a square in here? No. I do. I have more than that, right? I have more than 2 squared. I actually have 2 cubed. So I have a square with some extra, a square and a spare. Right, why not? So if a square cancels out a square root, right, don't I have at least 2 squared? Then the square root will be canceled, and I just get 2. But I had a 2 left over, right? I also have a 3 in there. Do I have a square of the 3's? No. Then it stays right where it is. And so I have 2 times the square root of 6 as my simplified form. Now, you guys hopefully very quickly will become very quick with this. All right? But this is broken all the way down. We can even interpret it as division. How many times will 2 go into 3? 1 time, with 1 left over. So how many do I have on the outside? To the first power. How many do I have left on the inside? To the first power. Is that okay? All right. So what if I wanted to simplify the square root of 80? So what should we do? Well, break 80 down any way you see fit. This is going to be where those multiplication tables some of you learned, it's going to give you that leg up. 10 and 8, which can both be broken down. 8 is 4 and 2, or even we could say 2, 2 and 2, right? 2 and 5 gives you 10. Right? You guys agree? So I have 2 to what power? 2 to the 4th, right? So do I have a square?
Yes.
Yes. Do I have another square? Yes. And then I have left over, right? So this means on the outside I'd have 2 squared, and on the inside I'd have 5, which is 4 square root of 5. Right? So I cut a step down, and we can even cut another step down from here. Right? From the prime factorization, do you see how I can jump to the end? Bring a 2 out. Bring a 2 out. That makes 4, multiplies to 4. Leave a 5 underneath. What if we want to simplify? Let's say 216. Can we break it down?
Of course.
As you get your calculators out. That's okay. No judgment. I mean, if nothing else, what do you know for sure? 2, right? Do you guys know your divisibility rules? Is 16 divisible by 4? Then so is 216. Whenever the number made by the last 2 digits is divisible by 4, so is the whole number. So we know 4 will go into it. Right? The digits add up to 9. Is 9 divisible by 3?
Yes.
Then so is this number divisible by 3. Is 9 divisible by 9? Then so is this number divisible by 9. Right? You got all those nice little divisibility things out there. So let's say, I don't know, worst case scenario, you're like 2, that's all I got. 2 would leave what? All right. What goes into 108? 9 goes into it 12 times. If you take 108 divided by 9, the remaining factor is 12. You guys agree? 9 breaks down. 3 times 3. 12 breaks down.
6 and 2.
2 and 6. 6 breaks down. 2 and 3. There's no rule that says you can only break it down 2 factors at a time, right? But that works. So look at what we have. Look at your dead ends. We could call this a prime factorization tree, which is cute because it kind of looks like a tree. Right. Do I have squares?
Wait, yes.
There's a square for 2. There's a square for 3, right? Now, do I have extra? Sure, but what happens to extra?
Put it on
You just leave it underneath. So what can I bring out?
2 squared and 3 4.
I can bring out 2 once, 1 pair. I can bring out 3 once, so 2 and 3 brought out make 6. What's left underneath? A 2 and a 3, which make 6. You guys see what I did there? Is that okay? All right. What if I want to break down the cube root of 540? Because why not? So let's do its prime factorizations. Right off the bat, I would think 54 and 10 would probably be the easiest to see, right? But you know, I'm not the greatest example.
90 and 6.
You guys know if it ends in 0, it's divisible by 10, right? Yes? Nobody shocked by that one? Okay. So I think 54 and 10 makes sense. 54 can be broken down into 9 and 6. 10 can be broken down into 2 and 5. 2 and 5 are primes. That's the end of that branch. 9 and 6.
3 and 3.
3 and 3.
2 and
2 and 3. There's my prime factorization. Now, this time I have a cube root. What cancels cube roots? Cubes. Do I have any cubes?
3.
Let me change color. I have 3 3s. That's a cube, isn't it? Anything else that I have cubes of? No. So what can I bring out?
3.
I can bring out a 3. I have 1 triplet. So bring it out once. And what can't I bring out?
2 squared and 5.
Yep, I can't bring out the 2, or the 5, which makes 20 left underneath. And we know this is simplified because 20 breaks down into a pair of 2s and a 5. And what do we need to cancel a cube root? A cube, which we don't have any cubes inside 20. Is that okay? So 3 cube root 20. What if we are given the square root of 180x to the 7th? Now, in this example, variables actually wind up being easier than the numbers, right? Let's break the number down. What do you got for 180?
10 and 18.
10 and 18. I mean, you could always do 2s at a time, but, you know, fundamental theorem of algebra says eventually you'll get there. Both of these break down. What do you got for 10? 2 and 5. 5 and 2, same thing. What do you got for 18? All right. 6 and 3 is fine, but 6 breaks down into 2 and 3. This is a square root, so what do I need? Squares. Do I have squares? I have a 2 squared and a 3 squared. So what do I bring outside?
2 times 3.
Yep. 6. What do I have left underneath?
5 times 6. That's 5.
Just 5. I have a 5 there. Do I have a square? Nope. Just one lone little 5. Under it goes. What about the x? Do I have squares?
Yes.
Yeah. How many? I have 3 squares, right? 2, 4, 6. And then I have 1 extra. So I can bring outside x 3 times, so that's x cubed, and I'd leave underneath x1. Again, it's a simple case of division. If you think about it on the side, how many times does 2 go into 7? 3 times. Remainder? 1. So I brought out an x cubed. I have x to the first left. Is that okay? So what if we had the cube root of 378 v to the 6 w to the 20th power? Let's break down our numbers. What do you got? Well, the digits add up to 18. Is 18 divisible by 9?
Yes.
Then so is this number. So 9 and what?
42.
42. Right? The answer to the question of the meaning of life and everything. If you have culture, you got that. If not, read a book. All right, 9 breaks down. 3 and 3. 42 breaks down. 6 and 7. That's good multiplication tables right there. I mean, if all you got is 2 and 21, you'll get there too. All right, that's fine. So 3's done. 6 is 2 and 3. 7's done. This is our prime factorization. You guys agree?
Yeah.
Do I have pairs? Do I have, sorry, I don't need pairs, I need triplets. Do I have cubes in here? I do have 3 cubed, right? That's it, right? So what can I bring out? 3. But what's left under? 14. The 2 and the 7 make 14. Is everybody on board? Because I don't have a cube for 2 and I don't have a cube for 7. What about v? Do I have cubes of v? How many? Two of them.
Oh, cubes. Yeah.
I have 2 cubes of v. Any left over? No. Right. How many times will 3 go into 6? Twice, with a remainder of 0. So I can bring 2 v's out, no v's left. Is that okay? Do I have cubes of w's?
6. 6 with the remainder of 2.
Yep, 6 cubes would make 18 of them, so that means a remainder of 2. You guys agree? How many times will 3 go into 20? 6 times. Remainder 2. You guys see how this simplification process is working? Let's try a 5th root. Right, we'll be bold. We'll do a 5th root. (128x to the 12th) y squared z to the 20th. So let's look at 128. All right, the digits add up to 11, so that's not divisible by 3 or 9. But 28 is divisible by 4, so guess what? So is this. 4 and 32. 4 is 2 and 2. 32 is 8 and 4. 8 breaks down.
4 and 2. 3 times.
Indeed, it's okay to break it down smaller. 4 breaks down into 2 and 2. What am I looking for here?
Hold on to it.
Fifths.
Fifth powers, right? Do I have a fifth power?
Yes. Yeah, 7.
I do. With some extra, right? So what do I bring out?
2, 2.
I bring out a 2. What do I have underneath? 2 times 2 is 4. I have a square left over, but a square is not enough to cancel a fifth root, right? You guys agree? All right. Next, we'll look at x. Do I have fifths?
2.
I have 2 of them, right? So that means I have x squared. How many left over?
6 squared.
You guys agree? I have 2 fifths. That makes 10 total with 2 left over. What about y? I don't have enough, so it just stays where it is. Y squared stays underneath. None come out. What about z? I have 4 fifth powers, so that means I have z to the 4th. Any left over? No, indeed. Right? 5 goes into 12 twice with 2 left over. 5 goes into 2 not at all, so you just have 2 left over. Oops, that's this one. And 5 goes into 20 4 times with a remainder of 0. None left over. All right, let's see some Nick action. How do you feel about simplifying radicals? Even with the big bad letters in there, which always freaks people out, those are actually the easier part, right?
No.
Oh, okay. And, you know, your mileage may vary. All right. We'll try one more for you. Let's do a fourth root. I don't think we've done a fourth root, right? Let's say we have a fourth root of 96 x to the 7th y to the 19th. Why not? So you guys take the reins. Tell me what to do.
It goes into 96.
What does go into 96?
3, 32.
3 and 32 is 1. All right. Any combination, 2 does go into it as well. All right. But she had more confidence, so I went with hers. Where do we go from here? 16 and 2 works?
4 and 4.
Yeah, 4 and 4. Hopefully that didn't shock anybody. Each of those breaks down. 2 and 2. All right. So what shall I write this equal to? All right, 2, 4 through to 6. You guys agree? Is everybody on board?
Where are you getting the 6 from?
All right. So what do we need to come out of a fourth root? What cancels a fourth root?
4.
A fourth power, right? Do I have a fourth power?
The 2s, right?
Yep. But I have an extra 2, don't I? I also have a 3 that's not part of a fourth power, right? Not part of a quartet. It's a sad little violinist. So if I have a 2 and a 3 that can't come out, they stay under. But 2 and a 3 makes 6, because it's all multiplication. All right, good question. What about x? 1 out. 3 left. You guys agree? What about y? 4 out. 3 left. So we are good. No factors of fourth powers are left under that fourth root. Right? 6 is 2 to the first, 3 to the first. X cubed, y cubed. None of those have any fourth powers left over. All right. So once we're comfortable simplifying, next step, in 18.4, we have addition and subtraction of radicals. Right? Once we've defined them, once we can simplify them, next thing up is being able to add them and subtract them. All right. So, in order to add or subtract radicals, we introduce the term like radicals. Okay? So, how do I know if two radical terms are like radicals? There's two components. In order to be like radicals, they must have the same index, right? What do I mean by index? What's the index of a cube root? 3. What's the index of a square root? 2. Right? Do they have the same index, a cube root and a square root? No. So we can't add cube roots and square roots. All right? The second thing is they have to have the same radicand. What was radicand? It's whatever's underneath or inside the radical sign. All right? Now, if we have, for example, two square root of 7 plus 3 square root of 7, are these like radicals?
Yes.
Are these like terms? Like terms has to do with x's. Neither of these have an x in it, so they are like terms, right? Since they are like radicals, if I have 2 square roots of 7 plus 3 more square roots of 7, I have 5 square roots of 7. Substitute square root of 7 with banana. 2 bananas plus 3 bananas? 5 bananas. Bananas didn't suddenly mutate into something else, right? So the square root of 7 isn't going to change either. If you have 2 square roots of 7 plus 3 square roots of 7, that's a total of 5 square roots of 7. All right? Don't let your bananas mutate. Good life lesson. Now let's compare this. If I have square root of 2 times x plus square root of 3 times x, are these like radicals?
No.
These are not like radicals. However, are they like terms? These are like terms. Okay? They're both x terms. So in this way, we could even think of it as factoring the x out. So if I combine square root of 2x plus square root of 3x, I wind up with square root of 2 plus square root of 3, parentheses, x. Is that okay? They're like terms, so we can just write it as one x term, but they're not like radicals, so we can't squish those two square roots together. Why aren't they like radicals? They do have the same index, don't they? Their index is 2, but what's different? Their radicands are different. Right? 2 and 3 are not the same. Hopefully that doesn't shock anybody. Such as in a relationship. 2 and 3 are not the same. I'll let you figure that one out. All right. What if we had, for example, (8x plus square root of 5x squared? Are these like radicals? I mean, I just wrote 3 letters up there that tells you they are not. Are they like terms? One of them's an x term, one of them's an x squared term. Those are not like terms. So they're not like radicals, they're not like terms. What can we do with this? Nothing. Sometimes the hardest thing for you guys to do. All right? This is it. If they're not like radicals and they're not like terms, there's nothing more to be done. Now, if I have 8 square root of 13 plus 2 square root of 13, can I add these together? Yep, because they are like radicals. Therefore, I get 10 square root of 13. Right? 8 bananas plus 2 bananas is 10 bananas, right? It's not going to change into strawberries. Right? What if I have (9 square root of 10 minus 11 square root of 10? -2 square root of 10. All right. If you have 9 bananas and have to spend 11 bananas, you are in debt 2 bananas. All right. To one very angry gorilla. Okay, let's level up. What if we have 15 cube root of 2x minus 7 cube root of 2x? Eight cube root of 2x. You guys agree? They're like radicals. What's the index? 3 for both of them. What's the radicand? 2x. Since they have the same index and they have the same radicand, they're like radicals. They're also like terms, so we can add them together, or in this case, subtract. That's the same thing, unadding, right, if you will. What if I had 6 square root of 10 plus 3 cube root of 10?
You can't do nothing with
You can't do anything with it. Why not?
that. Not the same index.
They're not like radicals because they don't have the same index. That's it. That's all you could do. Walk away. Right? What if we have 7 fourth root of 3x minus 2 fourth root of 3x plus fourth root of 3x. You guys agree? Was it just because he sounded so confident in saying it?
Because isn't there a 1 in front of it?
Yes. The coefficient here is 1 on that last term. Are they like radicals?
Yeah.
Yeah. Then we wind up with 7 minus 2 plus 1, which is 6. Fourth root, 3x. Let's say I have 5 square root of x plus 6 square root of x minus 5 square root of xy.
11 square root of x minus 5 square root of x.
I heard 11 square root of x
Minus 5 square root of xy.
minus 5 square root of xy. That's it? I know. Crazy. Although, the 3 of them are not all like radicals, because what's different? The radicand, right?
With x, y.
The first 2 are. What's the index? 2. The radicand? X. Since they have the same index and the same radicand, those first 2 are like radicals, therefore we can add them together. So we get 11 square root of x, and that minus 5 square root of xy just comes along for the ride. I'm telling you guys, don't overcomplicate it. If it doesn't go, it doesn't go. Move on. Okay. Now, that being said, I'm just about to complicate your lives. I mean, where would you be without me to give you something to do? What if we had 3 square root of 20 plus 5 square root of 45? At first blush, these don't appear to be anything that we can work with, right? Except we're combining what we did last section with what we did this section. Are these like radicals right now? No. However, do they simplify? Oh, snap. What do you got for 20?
2 and 10.
2 and 10 is fine. Eventually you'll break it down to the same. What do you got for 45? 9 and 5. I knew y'all judged by 9, so I fixed it. So, can I simplify 3 square root of 20? Yes. What do I get?
But you have the square of
6
all of them.
square root of 20 plus 15.
So why is this 6 square root of 5 for that first term?
3 times 2.
Yep. I have a pair of 2's. That's a square. Bring it out. There's already a 3 out there, so that makes 6. Meanwhile, I have the 5 with no pair. All right? Forever alone. I have squares of 2's, right?
Yeah. Well, I was looking at it as a whole because we were
It's all right. We'll get there. When we looked at it as a whole, we couldn't do anything. This is kind of like when we did GCFs. What about in the second one?
15.
15 square root of 5. Again, it's a square root, so do I have a square? Yeah, I've got 3 squared. So I bring a 3 outside. There's already a 5 there, so that makes
21 square root of 5.
15.
No, we
Oh, yeah, okay.
Yeah, when you add them.
I see what you did.
Yeah.
Now they're like radicals. 6 square root of 5 plus 15 square root of 5 is, she said, 21 square root of 5.
I'm lost.
In the second one, right? It's a square root, so that means squares will come out, right? Do I have a square? I have 3 squared, so I can bring out a 3, right? You agree I can bring a 3 out. But what's already out there? There's already a 5 in front, right? So if I bring a 3 in front, what does that give me? 5 times 3, right? It's all multiplication. So 5 times 3. Meanwhile, this 5 doesn't have a pair. There's no square there, right? So this lonely little 5 stays underneath, forever alone. So we get 21 square root of 5 is our final answer. Let's see another one. 1 is never enough. What if we needed 3 square root of 12x minus 6 square root of 27x? Again, at first blush, these are not like radicals. You guys agree? However, we can simplify. For 12, we've got, that's fine. She said 2 and 6. We went with it. 6 breaks down into 2 and 3. You'll get to the same place. 2, 2, and 3 is the same thing as 2, 3, and 2 is the same thing as 3, 2, and 2. What about 27? 9 and 3. Where 9 is 3 and 3 itself. You guys agree?
Yes.
So, what do I have from that first radical? What can I bring out? I can bring out a 2, which is going to give me 6. It's all right. That's why we're doing it. Right? What's left under? 3x under the square root. You guys on board? There's my square. I have 2 squared.
Why is it 3x? Oh, the 3 was left.
So I still have that lonely 3. It's nice you try to find him a mate, but sometimes it doesn't work. All right, so on the second one, I've got a square. I can pull out 3. There's already a 6 there, so that makes 18. What's left? 3x. So there's my square of 3's. So I bring a 3 out. There's already a 6 there, so that's 18. What's left? That third wheel and the x. Are they like radicals now? Yes, indeed. 6 square root of 3x minus 18 square root of 3x is negative 12 square root of 3x. Are you guys okay? All right. Let's go ahead and look at 18.5. Now, multiplication of radicals. We've already made a rule for this, right? We were just using a rule in one direction. So the rule that we developed the nth root of a times b is what? Nth root of a times nth root of b. Well, everything in math is a two-way street. So this means nth root of a times nth root of b is nth root of AB. So we have a rule for multiplying radicals together. All right? Now, in order to add and subtract, what did we have to have for radicals? They had to have the same index and they had to have the same radicand. So we could only add or subtract like radicals. However, in order to multiply radicals together, what's the only thing we need? We need the same index. That's it. All right? Is it okay that the radicands are different? Yeah. In fact, what do we do with them? Just multiply them together. So, if I have square root of 5 times square root of 11, can I do this multiplication? Yeah. They're both index 2, so I can write it as one big happy square root of 5 times 11, which means I have square root of 55. You guys agree? And voila, you've multiplied these two square roots together. Similarly, can I multiply cube root of 6 times cube root of 10?
Absolutely.
We do have like radicals, or not like radicals, sorry. We do have the same index, and therefore we got cube root of 6 times 10. So that is cube root of 60. And just like that, we've multiplied two cube roots together. Okay. What about square root of 5 times cube root of 4?
They don't have the same index.
They don't have the same index.
So no.
They also don't have the same radicand, so that's it. They just are what they are.
I thought that doesn't matter.
Do think back. Let's do. What if I had square root of 5 times cube root of 5? I don't have radical rules for that, right? We don't have radical rules. However, we can still change that to its exponential form. That's the same thing as 5 to the 1/2 times 5 to the 1/3. You guys agree? You forgot about that, right? Long weekend. Since we're multiplying like bases, we can, in fact, add the exponents. That's 5 to the 1/2 plus 1/3. You guys agree? In order to add fractions, we need common denominator, which would be 6. So this would be 3/6 plus 2/6. So we wind up with 5 to the 5/6, which is the 6th root of 5 to the 5th power. You guys recall? So what makes this nice to illustrate is that we like having radical rules, because radical rules are much shorter than what we have to do here. All right? So radical rules are a little bit of a time saver. But it doesn't always work, so we do have to keep in mind those broader rules that we have. I will warn you with the example that I want you to do this on. All right? So you will be warned. I won't just throw it at your face until you figure it out. All right. So what if I had the 7th root of 2x times the 7th root of 6x cubed? I've thrown the variable back into the mix. 7th root 12x to the 4th. You guys all comfortable with that? Is that simplified?
Probably not. I don't know.
Yeah, it's a 7th root. So what do you need in order to cancel a 7th root? 7th powers, right? Well, 12 breaks down into 4 and 3, which is just
Told you.
2, 2, and 3. Do I have a 7th power there? No, I have 2 squared, but that's piddly compared to what we need. So what comes out? Nothing. It all stays under. However, if I have the 4th root of 125x squared times the 4th root of 5x cubed, right? Multiply them together, and what do we get? 4th root, 625, x to the 5th. You guys agree? Is everybody okay with that? But does this simplify? Yeah. The last one didn't. This one will. Right? Well, if nothing else, you know that breaks down into 125 times 5, which breaks down into 5 times 25, which breaks down into 5 times 5. What do I need to cancel a 4th root? 4th power. Do I have a 4th power? So what can I bring out? 5. Any left under? No. What about the x's? Do I have 4th power? How many? One of them. So bring one of them out and leave one of them under. So it simplifies to 5x, 4th root of x. Is that okay? Right. Now, you could simplify, then multiply, all right? But you still have to check to see if it simplifies again. So I'd go ahead and multiply and just simplify in one step. You know, just my pro tip, what do I know? So what happens if I want to multiply 2 square root of 3 times 4 square root of 6? That's all multiplication, right? So if I write it out, that's a 2 times the square root of 3 times a 4 times the square root of 6, right? Multiplication is commutative, meaning the order I multiply in doesn't matter, right? So couldn't I do 2 times 4 times square root of 3 times square root of 6? Same thing, right? What's 2 times 4? Okay, good confidence. What about the square root of 3 times square root of 6? Square root of 18. Now again, I wrote all the steps out for posterity's sake since this is the first time we've done it. But how do I multiply two radicals together? It's easy. Outside times outside gives me the outside. Inside times inside gives me the inside. Is everybody okay with that? So you don't have to write this out. 2 times 4 is 8. 3 times 6 is 18. The 8 is outside. The 18 is on the inside. However, this does simplify. Yep. 18 breaks down into 6 and 3 is fine. Where 6 breaks down into 2 and 3. It's a square root, so I need a square. Do I have a square? So what can I bring out? a 3, which leaves me with 24 square root of 2. You guys agree? I have a 3 squared, so I bring the 3 out. There's already an 8 there, so that makes 24. And then I have a lone 2. It's not part of a pair, so it stays underneath. What if I wanted to multiply 10 cube root of 16 times 5 cube root of 2? All right. We got 50 cube root 32. Everybody on board with that? All right. Does this simplify? Yep. 32 breaks down. 8 and 4 is fine. There's other options as well. 8 is 2, 2, 2. 4 is 2 and 2. I have a cube root, so what am I looking for? Cubes. Do I have cubes? So what can I bring out? I can bring out a 2 once. I have 1 cube, right? That leaves me with 100. But then I'm left with cube root of 4. Once I pull out my cube, I have 2 2's left. That's not a triple. Right? So that's not enough to come out. 100 cube root of 4. Everybody okay with that? Let's say we take four times square root. I'm sorry, fourth root. I don't even know what I was saying. Fourth root of 4x squared y times the fourth root of 8x to the 6th y cubed. Fourth root of 32 x to the 8th y to the 4th. You guys agree? 32. We just broke that one down, didn't we? It's 2, 2, 2, 2, and 2. What am I looking for? Fourth powers. Do I have it?
Yes.
Then what can I bring out? A 2. But I have an extra one, right? Is everybody on board with that? Right? You guys were a little concerned at first. How are you feeling about it now? Better? I mean, that's what I'm here for. Okay? To make you feel better after I hurt you. We can pull out an x squared. We can pull out a y. Any of those left under? No. I have 2 fourth powers of x. So that's x squared. No remainder. I have 1 fourth power of y. None remaining.